Good morning. Welcome to class May 1st, Friday. We've already had two assignments for this week, so we're not allowed to make more than two assignments mandatory. So if you do this one, I'll count it as an extra grade that can go towards your grade, or if you're missing a grade, I can replace that grade, something along those lines. I still recommend doing this one because, it's the AP test is coming up in 2 weeks. We're in May. May 14th, so we're right there at the end of the year. Don't kind of stop working now. Now's the time to really just kind of work for 2 weeks and then you're free. No final exams. Once you've done your AP test, you're done. And so, yeah, just kind of keep working. We're going to go through the rest of the AP questions. We have a few more, and then the week of the AP test, we're going to do some setting up of your formula chart and different types of cheat sheets and kind of trying to draw things together. All right, so let's just start here. So we have a question, we have a spring right here, we have a mass M that looks like it's moving this way along, and then it looks like we're dropping a mass 2M on top of that. So block P of mass M is on a horizontal frictionless, that's good, surface, and attached to a spring with a spring constant K. The block is oscillating with a period TP and amplitude AP about the spring's equilibrium position x naught. So we're at equilibrium right here. So the spring is not stretched or compressed at this moment because, again, spring equilibrium position is saying when the spring is not stretched or compressed. System equilibrium will be when the net force is zero. And if it's a horizontal frictionless spring, then our system and spring equilibrium will be at the same point. That's only really when we have that vertical spring that things get messier. A second block, Q of mass 2m, is then dropped from rest and lands on block P at the instant it passes through the equilibrium position as shown above. Block Q immediately sticks to the top of block P. So this is pretty important. It's not sliding around. It's collides and immediately the collision is done. Mathematically, this makes things a lot easier. Otherwise, you have to analyze the whole motion while they're sticking together, and things get really messy when you do that. And the two block system oscillates with a period TPQ and amplitude APQ. So A wants us to determine the numerical ratio of the period with both masses divided by the period with just one of the masses. All right, so we're trying to find period. And we might as well just set up our equations here. So we have period of a spring is going to be 2 pi square root of mass attached to the spring divided by spring constant of the spring. Now again, they're probably not going to have as much math where you have to sit here and calculate all these, but I could easily see them asking questions about the period. I could easily see them asking questions how the period will change as this happens. So is the period going to change when I drop the other mass on it, and why?
Dạ để đây.
The mass of the object has gone up, so yes.
The mass of the object has gone up, so yes. So more mass, so the period is going to change. So we can do period for just mass P would be 2 pi. This has mass M, spring constant K. Then the other one is with both masses that they call TPQ is going to be 2 pi. But now the two masses combined together, so what's our total mass now? (3m). All right, and then we're going to just divide these two. I could see them asking you a question like this where you're supposed to get the ratio. So I would just have a piece of scratch paper next to you. I don't know how much they're going to make you do that, but The more things you have readily available, the less you're going to be running around your house trying to find things while you're taking the test. So it'd probably be good just to at least have some scratch paper and pencils just in case. No, that's fine. I was wondering what that noise was. I honestly wouldn't have even known it was you if you didn't say anything. 3m divided by k divided by 2 pi square roots of mass m divided by k. So pretty quick, we see 2 pi divides out. Divide by a fraction, I invert and multiply. So this is going to be the square root 3 mass divided by spring constant times the reciprocal is the square root of spring constant divided by mass. Square root of k divided by square root of k divides out. Square root of m divided by square root of m divides out. And I just end up with square root of 3. And again, like Tam showed, you can go through and figure out your shortcuts. I don't know if whatever they read this in, the formatting is going to work well like that. So if you have to type something like this out, you could do square root 3. I think everyone should understand that. That's used pretty commonly in programming, or at least the ones I use. Yeah, you did 1 over the square root of 3. Yeah, if you do the wrong thing divided. And then, yeah, probably not going to do so much math here. It just says determine the numerical value. Since it said determine the value, we don't have to explain it with words or anything. But more likely than not, this year they would ask a question, how does this change? How does the period of the spring change? And we could just get to the point where we see, oh, well, we increase the mass attached to the spring, so we expect the period to be bigger, so it's going to take more time to go back and forth. Or they could ask about the frequency. It takes more time, so it's a smaller frequency, less events happen per second, less frequent. Or they could say how much time it takes to go from one side to the other. The time goes up. There's a lot of questions they could ask here without making you do the math. So again, that's why we're going to keep doing things, even if it doesn't necessarily, if it's probably not going to show up on this year's test, because there's still good practice. So I think it was just, yeah, you just got 1 point. You got the correct answer or you didn't. Which is really unusual for the AT exam. But every once in a while it happens where it's just you either get the answer or you don't. So then B. So since that was 1 point and this is 7 points, that means all of our points are going to come from this explanation down here. So the figure is reproduced above, so I showed it again. I think they wrote this on a second page on the actual AP test. How does the amplitude of oscillation for APQ, so the amplitude with both masses of the 2-block system, compare with the original amplitude of block P alone? Now, again, when it comes to ranking, let's start by explaining things first before we even get to our ranking. So in a clear, coherent paragraph length response, again, paragraph length response is like the wording is not paragraph response. It's a response that's the length of a paragraph. So you do need words in there. Try for complete sentences, but it doesn't actually have to be complete sentences, and it doesn't even have to be a paragraph. You can write bullet points for this, and you still get those. Again, you can also include diagrams and or equations and explain your reasoning. All right. So, where should we start with this? Any ideas? There's a pretty big concept we should start with here. And it has to do with when I drop the mass onto the other mass. Mechanical energy. All right, it is dealing with mechanical energy, yes, because amplitude is the maximum distance, and we are doing momentum. What does momentum have to do with this? So those are right. So we're using energy and momentum here. That's exactly what we're doing. I'm going to start with momentum, though. What type of collision is this? So this is an inelastic collision. So that's where momentum comes in, is collision type. So an inelastic collision, that means that mechanical energy is lost, and specifically we're at equilibrium. So what type of energy do we have here? So we're at the equilibrium position. That means that we have kinetic energy. Kinetic energy at that x naught position. We lose kinetic energy. So the block lose kinetic energy, which means we have less spring potential energy at the maximum displacement. So if we have less spring potential energy, well, let's look at our spring potential energy as 1/2 spring constant times displacement from equilibrium squared. We didn't change 1/2, that's a number. We didn't change spring constant. So if we have less spring energy, we have less displacement from equilibrium. That means we have a smaller maximum displacement. And maximum displacement is our amplitude. So we have a smaller amplitude. So going through. So an inelastic collision. So we're losing mechanical energy. And specifically, we have kinetic energy here. So we're losing kinetic energy. So the block loses kinetic energy. So we have less. So we lose kinetic energy at our equilibrium position. So we have less spring potential energy at our maximum displacement. So our spring potential energy goes down. That means we have a smaller displacement from equilibrium. So we have a smaller maximum displacement. So we have a smaller amplitude. And now we can finally rank things. So the amplitude with both of these is going to be less than the amplitude of just mass P. And only a few sentences here. There's really few answers I can imagine you needing more than 4 sentences. Honestly, most of your answers are probably going to be around like 2 to 4 sentences. If you're really concise, you might be able to do something in 1 sentence. Usually, no. Usually, you're going to need at least 2 sentences for something. Rarely are you ever going to need to write more than 4 sentences. So if you find yourself writing like 6, 7 sentences, something went kind of wrong. You're rambling and you're missing the point somewhere. So let's look at our points. So this is 6 points. So applying conservation of momentum, and then the post-collision speed is decreased, or actually solving for that. So we could actually go through and use our conservation of momentum to find a lower speed. So those are 2 points. So conservation of momentum, just talking about momentum there, it's an inelastic collision, and so we lost energy. We lost kinetic energy. Or just saying that the collision is inelastic. All right, and then implying kinetic energy as decreased or calculating it. So the stating or implying, I didn't ever explicitly state that, but we implied that kinetic energy of the block right after the collision equals the maximum potential energy of the spring. And then stating or implying the maximum potential energy is reached when the displacement from equilibrium is at amplitude. I more implied that. I said less spring potential energy at the maximum displacement. So I never explicitly said that's where it happened. I guess kind of, there's more implication. And then this last one is logical, relevant, and internally consistent argument. So logical. I mean, it follows relevant. We're talking about energy and momentum. You're not over here talking about like rotational motion or some completely random thing. Internally consistent. So you can't contradict yourself. You can't say we have less energy here and then more energy there. So if you say like we lost energy, then we gained energy, that would be a case of not internally consistent. I would argue internally consistent if you say somehow we gained energy and then you say we gained energy here and then you're still wrong, but I would say that's internally consistent. Like you're wrong, but you're consistently wrong, as opposed to bouncing back between being correct and incorrect. It addresses the required argument or question asked. So as long as you're talking about the amplitude and you're addressing it and you're going on about things that are relevant to the question, and then you follow the guidelines, so pretty much you actually explain things in words, then you get this point. So you can get everything here wrong and still get this last point. And then we can get an alternate solution for B. So another way is you could have said there was a frictional force. I kind of disagree with this statement because if it's an immediate collision, there's no distance the frictional force acts over, which I don't know. Physically, an immediate collision kind of makes no sense, and this argument kind of breaks down there due to the assumption. But yeah, you could have said there was a friction between the two blocks. All right, questions on the scoring of this? I think this one could have gone well. Like I'm hoping more people got points on this, but obviously, I mean, there's a lot of easy places to go. You didn't get any points. It happens. It's a really weird way of showing a collision. Yeah, I guess I am biased. Sometimes I like think there is. I mean, I think this is kind of obvious with when I make a test. I'm like, I think I made this one easier, and then no, it's not. I mean, I guess I'm just biased. I've obviously been doing physics for over half my life, so it can be hard to see what's harder and easier. But yeah, I guess that's the hard thing is that seeing this as an inelastic collision, because normally we don't collide this way. I can see that being hard. The other thing that I could easily see asked, what happens if instead of dropping this at the equilibrium position, what would change if I drop the mass when it's at its maximum displacement? So what if I drop this mass on the other mass when it was at its amplitude? Would that affect the period equation? So if I drop the mass at the amplitude instead of at equilibrium, the period wouldn't change, right? Because I didn't change anything about mass or spring constant. So I could ask a question like that. If I dropped it at the amplitude, the period won't change because it's still increasing to 3 and we would get the same ratio. It would be the whole simple harmonic motion thing, how it doesn't matter how far away it is, it's still going to oscillate with the same amount of time through equilibrium, right? It'll oscillate slow if it's right around equilibrium or fast if it's far from equilibrium. But those times are going to be the same. The more difficult one would be part B. If we drop the mass on the equilibrium position, I mean, not on equilibrium, but at the amplitude, we would all of a sudden see that there's no kinetic energy at the amplitude, so there would be no kinetic energy to be lost. And so if we dropped it at the amplitude position, the amplitude would stay the same because we're not losing kinetic energy because it's an inelastic collision, but there's no speed, so its speed stays 0, and we would still have that maximum spring potential energy because we're still at that maximum distance, things like that. All right, this thing will do. Hopefully this next one will a little bit better. This one's weird. I honestly feel like the AP test, they were trying to make it easier for a little while, and then I think they felt like they made it a little bit too easy, and then they started asking questions like this. This one is interesting. All right, so here, this was the first one from the last year's AP test. So we have identical blocks 1 and 2 are placed on a horizontal surface at points A and E respectively as shown. The surface is frictionless except for the region between C and D where the surface is rough. I honestly don't know why they put that, like a random rough surface at C and D. Beginning at time TA, block 1 is pushed with a constant horizontal force from point A to point B by a mechanical plunger. So constant, notice that's underlined, clearly important. So it's not acting like a spring, right? A spring does not apply a constant force. This is different than a spring question. Upon reaching the point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface towards block 2. Block 1 collides with and sticks to block 2 at point E, after which the two-block system continues moving across the surface, eventually passing point F. So, yeah, so on the axis below, sketch the speed of the center of mass, and notice center of mass is underlined here. So when we're talking about center of mass, which mass are we talking about? Mass 1, mass 2, or both masses? What? Yeah, so we're looking at both masses here, and this is going to be tricky. This is legitimately a difficult thing to think about, even for people who've done physics for a little while. So we're looking at the average speed of these two masses together. All right. So we need to look at the average of the speeds between these two masses, not the average speed for the masses across the distance, but I would have to do speed of object 1 plus speed of object 2 divided by 2. So we're looking at the average speed along the entire thing as a function of time until the block passes point F at TF. So we have on our graph here, we have A to B when the thing is getting launched, B to C along a frictionless surface, C to D, we have friction, D to E, no friction before the collision, E is when the blocks collide, and then E to F, the blocks slide along without friction again. So here we have speed versus time. So this is a kinematics question. Not that we're using the kinematic equations, but it is kinematics. We have speed versus time. Now again, they can't really ask us to draw a graph like this, but that's not the important thing about answering a question like this. They could easily ask us this question, this exact same thing, and give us a graph and say, is it correct or not? So I imagine, while they're not going to have you graph things, I could easily see them giving you different graphs and say, is this correct or not? Why is this correct or not? Why is this wrong? Why is this correct? So don't just think, oh, there's going to be no graphs, so I don't have to look at graphs at all. It's still, they would just change the question from you draw the graph to you analyze the graph. All right. So what happens between A and B? What are some key words that happen between A and B? Force. So what's happening with that force? Well, what's the big important thing about that force? It is acceleration. It does cause acceleration, but how does it accelerate? So we start at rest. So it's placed on a horizontal surface. Time A, it's pushed. So placed there. It doesn't ever explicitly say at rest, I don't think, but it says place, so it starts at rest. Constant. Why? Where is constant acceleration coming from? That's the word I was looking for. We have a constant net force, so we have a constant acceleration. Speed can't be negative, so we have a straight line here from here to here. So normally, if this was a spring, we're going to see a very different thing. It would be a concave down curve because a spring has a larger force here, smaller force there. But because this is a plunger with some unknown system pushing it, constant force, constant acceleration, so constant slope on my speed versus time graph. So constant net force, constant acceleration, so constant slope on speed versus time graph. So see how easily I could turn this into a question analyzing the graph? I could just give you this graph and say, does this match what I wrote up here? And yes, it does match what I wrote up there. Constant net force means I have a constant acceleration. So I have a constant slope on my speed versus time graph. Yeah, and you can also throw in, it's normally good to throw in mass as constant. Normally they'll let you get away with implying mass is constant, but yeah, that is another important part of this because yeah, it could be a rocket. You have a firing rocket, mass is changing, and that's going to change your acceleration. Now B to C, what's happening to my speed between B and C? So we have a constant speed, so that's going to be a horizontal line here. So we have no force of friction, which means we have no acceleration, which means we have a constant speed, which means we have a horizontal line on our speed versus time graph. Again, if you're talking about this, don't just say straight line. Both of these are straight lines. You would have to say a horizontal line to show that there is no speed on my speed versus time graph. And again, remember that phrasing. You always want to say what type of graph. No slope on my speed versus time graph means a constant speed or horizontal line. All right, what's happening between C and D? So we have a decreasing speed. We slow down, so some lower amount. It doesn't give me values here, so I don't do any math. So negative acceleration. Yeah, constant negative acceleration. And we can't really say positive or negative acceleration. I would say acceleration to the left. One of the things, speed versus time, can't really tell us if the acceleration is positive or negative. All it can tell us is speeds up or slows down. Remember the weird case if I'm going left and I accelerate to the right, I'm slowing down so I can have a positive acceleration and slow down. So we are slowing down. So we have force of friction is not 0 newtons. So that means we slow down. Now, how are we going to slow down? How do we know that's constant acceleration? Constant friction force, because that's going to be coefficient of kinetic friction times normal force. And again, we do have the equal sign because we're sliding across the surface. So this slides across the surface. There's relative motion between the two surfaces. So that means we can use the equal sign in our equation, that magnitude of frictional force less than or equal to the coefficient of friction times the magnitude of normal force, equal to because we slide. So coefficient of friction, it doesn't say anything about a non-uniform surface, and we're not changing the weight of the object. So yes, we do have a constant slope from here to here. and I would be writing these out. It's not important to answering this question, but it's probably going to be more relevant to this year's test. So D and E, what's happening here? Constant speed, no friction. So our argument from here also applies here. So horizontal line. E to F. This is the one where I'm pretty sure people are most likely to mess up on. What's happening? It is an inelastic collision. What's happening to the average speed of the two masses during the collision? For identical masses. Why is the speed of the center of mass constant? This is, I mean, I don't know if you looked at the key or you just guessed, but it is constant. Momentum is conserved. The masses are the same. So let's look at that momentum being conserved. So I have mass 1 times that initial speed of 1. I'll just call that V naught. The other masses at rest is all equal to mass 1 times final speed plus mass 2 times final speed. It's an inelastic collision, so the final speeds are the same. They're identical masses, right? So I can just do mass M. It says identical blocks 1 and 2. So mv naught is equal to mv final plus mv final. So mass times initial speed equals 2 mass times final speed. So I could divide this over. So divide the 2, divide the m out, divide the 2. So the final speed is going to be half of the initial speed. So you might be thinking, why don't we go down to halfway to the bottom though, right? Yeah, so that's what we're thinking. We should have half the speed. But the thing is, we're looking at the average speed of the two masses, right? The speed of the center of mass. Of that center of mass. Which means the average of the two speeds. So let's look at before. For the average speed, and by the way, I'm using my initial speed is going to be like in here. I'm not talking about the initial speed completely when it's launched, but the initial speed is going to have to be somewhere in here after the frictional point. All right, so before the average speed of the two masses, and again, I'm not talking about average speed over the time span. I'm talking about the average speed of the two masses. So the average speed would be V naught plus 0, because mass 2 is at rest, divided by 2 is equal to V naught over 2. Now let's look at after that collision. That average speed is going to be, well, block 1 is going V naught over 2. Block 2 is going V naught over 2 divided by 2. V naught over 2 plus V naught over 2 is equal to V naught over 2. So the average speed of the two blocks does not change. So we're talking about the speed of the center of mass. In order to change the speed of a center of mass of two masses, I need some net external force. During this collision, all we have are internal forces, right? Because there's no friction, no air resistance, no like ramp making this speed up. We just have mass 1 colliding with mass 2. So we can look at it this way. When we have the collision, mass 1 changes speed because block 2 pushes on block 1. Block 2 changes speed because block 1 pushes on block 2. But if I look at the average of block 1 and 2, the force between 1 and 2 is an internal force. That internal force can't do anything to change the momentum of the total system. So if I look at block 1, yes, block 1 slows down. If I look at block 2 speeds up. But if I look at both blocks together, their average speed does not change. And another important thing about this statement is they don't change because they have identical mass. It gets a lot messier if the masses are not identical. All right. Joel, kind of see that, or is it still not making sense? Because that's a tough one. Even my first instinct was to say it drops down until you're really carefully looking at that. So there's a chance that even me reading that might draw this down to that without thinking if I didn't read that carefully enough. So if that makes you feel better about missing it. So we get 1 point for this first segment. Straight line begins at 0 at time A, increases to time B. It has to be a straight line. Then we have a horizontal non-zero line, so it's moving. We can't have a horizontal line at the 0 here between B and C. So horizontal to get the point. Then a linearly decreasing line from C to D, where we have our friction. Horizontal, non-zero, constant, but different value from the original segment. So I have to have this point is horizontal and non-zero, but it has to be different than this line. So if you just drew a straight line like this, you don't get that point because that's not the same. I don't think people probably would have done that one. And then the curve is continuous from A through F with a possible exception of time E. Yeah, so continuous, our speed isn't changing instantly. We're not going from here in the discontinuity in the graph. If the speed changes at time E, the fourth point is not earned, while this point may still be earned. Oh, no. That's what it was. Sorry, I misread this. So this fourth point is you have to have a horizontal line this entire time. Continuous, yeah, you have a continuous speed versus time, but your position time is going to have discontinuity. Not position time, your acceleration time is going to have discontinuities. So the fourth point, you have to have a horizontal line from D to F, and then you get this point for all of the lines are connected to each other, and it doesn't care what this line does. So if you drew this line down, like decreasing here and then constant or something like that, as long as you just can't draw a vertical line there. If it dropped down over a small amount of time and then went like that, then you get that point, is what I think they're getting at. No credit is earned for a horizontal line along the t-axis. That's funny. Because there are times in the past where if you just drew a horizontal line like this, you could get some of these points, but they took that out where you can't just draw the horizontal line and get points. That makes me laugh. All right, so hopefully the first, second, and third points, hopefully y'all were able to get that. And then probably not the fourth point. I'm pretty sure most people miss the fourth point. But then hopefully the fifth point, that things are continuous and you don't have vertical lines. All right. B is a subtly very tricky question. The plunger is returned to its original position, and both blocks are removed. Now we have a uniform solid sphere is placed at point A as shown. What's the word that's coming to people's minds right now? Probably rotational motion of some form. Rotational, exactly. Yay, everyone's favorite. The sphere is pushed by the plunger from point A to B with a constant horizontal force directed towards the sphere's center of mass. Now, this is a very important statement. Directed, why are you not highlighting? Whatever. Directed towards the sphere's center of mass. Sometimes that lets me highlight, sometimes it doesn't. The sphere loses contact with the plunger at point B and continues moving across a horizontal surface towards point E. And which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. So again, let's go to our reasoning first before we check these off. So, what do I need for rotational motion to occur? First of all, what concept are we talking about here? So we're talking about torque. Very, very good. So it starts out at rest. We need a torque. So in order to get a torque, so I would start a little bit back from that. I would start with our angular acceleration is net torque divided by moment of inertia. So exactly, in order to have an angular acceleration, we need a torque. So we need a net torque to cause an angular acceleration to begin rolling. Or what did the question actually ask? No, we don't need to, not to begin rolling. To change to change angular velocity. That's what we're going for. Angular velocity. And angular acceleration. Not angular momentum, sorry. So there's a few ways of going about this. We could do our change in angular momentum is net torque times time, our angular impulse equation. Or we could do angular momentum as moment of inertia times angular velocity. So we could talk about this either way. If I have a net torque over time, my angular momentum changes, or just angular momentum as moment of inertia times angular velocity. So if I change my angular velocity, I change my angular momentum. Either of those paths should work. All right, so we need to figure out where we have a net torque. So what regions do you think we might have a net torque in? First of all, let's say what regions we definitely don't have a net torque in. I'm gonna say let's do B to C and D to E. We definitely don't have net torques, right? B to C and D to E. All of the forces acting on this object, we have our force of gravity down, we have our normal force up. These are balanced, they're from the center. I know my torque is radius times force times sine of the angle. So B to C and D to E, my net torque is equal to 0 Newton meters, which means I have a constant angular momentum. Those are the obvious ones. Now, Tam, you said A to C. So why are you saying A to B is not changing the angular momentum? So let's look at A to B next. Why are you saying A to B has no change in angular momentum? So let's look at our forces here. So like before, we have normal force and weight. These do not contribute a torque. Pushing against the center of mass. So we have an applied force by the plunger. And this is it, right? It's frictionless. So all forces act on the center of mass which means that R value equals 0 meters for all of these. That means our net torque is 0 Newton meters, and angular momentum is constant. All right, so this is back to that whole idea that we need to push at a distance from the center at an angle not directed at the center of the object in order to change the angular momentum, in order to make something roll. And again, the importance of friction to making things roll. So this whole question was designed to make you try to choose A to B as one of those times, as one of the position intervals that the angular momentum changes. But between A and B, this thing is not going to roll. If there's no friction, it's just going to slide across the surface. So that's not going to be part of it. So that just leaves C to D. C to D, is this thing going to change angular momentum there? How do we know radius is 0 meters? So we know radius is 0 meters because they're all acting 0 meters from our center of mass. So again, remember radius is the distance the force acts from the center of mass. So the applied force, I guess actually the radius isn't 0 for all of these. I should probably say. Yeah, you're right. We should say that the normal force acts from the bottom. If I'm being really careful here, the normal force is from here to here, and it's part way through. Yeah, I guess we should be more precise with our language. All right, so not all forces, but the force of gravity acts on the center of mass. Then we would have to see at the normal force and the applied force. Normal force and applied force push toward the center of mass. So for this one, we would see if we're pushing towards the center of mass, our angle is going to be 0 degrees. And then we get the whole sine 0 degrees equals 0. So torque equals RF sine 0 degrees. So we get 0 Newton meters. So yeah, that's really what we should have done for. We could have done this for all of them, by the way. They all act towards or away from the center of mass. So you could either use, if it's toward the center of mass, you could call it 0. If it's away, you could call it 180. Because again, we're always talking about the angle between radius and force. So if it acts along the radius, if the force acts along the radius, the angle is just going to be 0. But yeah, it's just, in order to make something turn, I'm not going to push towards the center to make it turn. If I want something to turn, I have to push along the side to make it actually roll. So I need to push perpendicularly to the radius in order to make it roll. If I push towards the center, it doesn't roll. So C to D, what's different from C to D? Friction. So we have friction acting along the surface to the right. So force of friction, and then again, you're going to be typing this, so I should probably just write out friction. So friction acts at a distance r from the center of the sphere at a 90-degree angle. And then so we would have torque caused by that force of friction is going to be the radius times the force of friction times sine 90 degrees. Sine 90 is 1. So we have radius times that force of friction. So here we have a non-zero net torque. So friction causes a non-zero net torque. Net torque, therefore angular momentum changes. And that's all due to the change in angular momentum is net torque divided times time. And out of all of these, you really don't need to write as much as I did here. Again, we really want to try to put this down into one sentence or less. So we don't need to go through this entire mess here. I would just kind of start with our equation that our change in angular momentum is net torque times time. You should be able to write that out, even if it's in words. Change in angular momentum equals net torque times time. So we can write that out. And then we can get to here and we can say A to C and D to E, all forces act towards or away from the center of the sphere, and the net torque is 0. And the angular momentum is constant. C to D has frictional force, which is the only force acting at a distance from the center of mass at a non-zero angle to the radius, which causes the net torque. And if we have a net torque, then our angular momentum will change. So I wrote way more here than you actually have to. So I would want you to try to kind of put this down into a fewer words. That's probably still going to be 3 or 4 sentences for this one. And I don't know if they're going to give you a full-on like paragraph length response like this. I kind of doubt they will. They're probably going to ask for shorter length responses. But yeah, try to get this down into 3 or 4 sentences. So we get 2 points. So correct answer. Again, they didn't say anything about getting the points there. For reasoning, change in angular momentum is caused by a net external torque. So something about needing a net external torque. And identifying there's friction from C to D, and that's the only force producing an external torque over the entire time interval from A to E. Yeah, the point is not earned if the statement is made the angular momentum or angular speed decreases between. Okay, so yeah, so if you say between C and D you lose angular speed, that's incorrect. You're actually gaining angular speed. So if they say you're slowing down here, which is true, your center of mass is going to slow down. It's going to move slower to the side, but it's going to start rolling faster. It moves slower to the side because it's turning that translational kinetic energy into rotational kinetic energy. So it moves slower to the side, but it begins rolling faster. So you can't say it rolls at a slower rate. That would be completely incorrect. And then here, this is a much better response than mine because it's really concise. So the sphere's angular momentum about its center of mass changes in the interval from C to D. There's friction between points C and D. Friction applies a torque in region C to D about the central axis of the cylinder to increase/change its angular momentum. I don't know why they said cylinder. I thought it was a sphere, but yeah. Something like that. I would also include something about the regions A to C and D. D through E have a non-zero net torque, something like that. Questions on this one or the other one? Did y'all do better on this one, or? Because these were 2 a little bit more out there questions compared to some of the other ones we've covered. Much better on this one. Yeah, hopefully. It sounded like you knew it was only C or D. Out of all, like, I expect people to guess at A and B. Okay, you did better on this one. Yeah, probably your points were a lot coming from this graph. Hopefully the graph went well, at least from here to here. Obviously, E and after, I expected a lot of people to miss that one. But yeah, just keep doing what you're doing. Write your corrected response. Grade yourself. Try to be more on the harsh side rather than the lenient side. Get this in, it'll count as a bonus homework grade. So if you do everything correctly, you'll average in as another 100 towards your grade. So keep it up. We only have about 2 weeks till the AP test. You won't have a final exam, so it'll all be done from there. So just keep working, keep trying. Try not to get demotivated. If you miss all points for something. It happens. I'd rather you miss the points here than when it comes to the actual test. But yeah, keep doing these. If you've missed any of the other assignments, get them in. If you have any friends that you know haven't been working, try to get on them to help them catch up. So that'll make it a little bit easier on me trying to get them to catch up. I'm going to really be pushing them next week. But yeah, other than that, everyone have a good weekend. Try to relax, not think too much about school or the world. Just relax, rest. But have a good one.
I actually have a lot to do.